So far, we've looked at nucleophilic reactions. So the carbon having a partial positive charge, a carbon compound with a carbon having a partial positive charge, which is attractive to nucleophiles. But when you have double or triple bonds, then you have carbons that have an excess of electronic charge, and they can themselves behave as nucleophiles. They can attack positive charges. We call those electrophilic reactions. So in an electrophilic reaction, the electronic charge in a carbon in a double or triple bond attracts electrophiles. And is typical of double bonds, is typical of benzene and aromatic compounds. And it can give rise to a very rich chemistry. For example, the chemistry of benzene is the chemistry of electrophilic reactions, and the electrons from the benzene ring attacking electrophiles. Electrophilic reactions involve essentially the same first step. The pi electrons, the electrons from the double bond, attacking an electrophile, a compound that has a positive charge or that has free orbitals that are able to accept the electrons from the double bond, or a proton, for example, and an intermediate carbocation is formed. When the pi electrons of a double bond attack a tetrahedral carbon, which is the electrophile, then you can have those pi electrons act as the nucleophile, and you have a nucleophilic substitution in which you have a carbon which you have the pi orbitals, the pi electrons, acting as the nucleophile. You have the carbon that has the partial positive charge acting as the electrophile, and you have the leaving group. And they can work in an SN1 or SN2 fashion depending on whether they go by an intermediate mechanism that involves the leaving group and the leaving group and the nucleophile simultaneously leaving and entering the molecule, or they can go by a carbocation, an SN1 mechanism. And you can have carbonyl carbons, the carbons of a carbonyl group, being attacked by a double bond by those pi electrons, and in a similar fashion as if it was any other nucleophile. So what happens once that carbocation has formed? As a summary, the electrons from the double bond of a carbon-carbon double bond, those pi electrons attack an electrophile, and the electrophile enters the molecule, and you form a carbocation. And then the next step is for that carbocation to react. And the way it reacts is in the presence of a nucleophile, either from water, either the counter ion to the electrophile, the counter anion to the electrophile, etc. And that results in the double bond disappearing completely. And the formation of single bonds, and both an electrophile and a nucleophile added to the two carbons that used to have the double bond. Sometimes an electrophilic addition is followed by an elimination mechanism, and the double bond is restored, but not in the same place where it was initially. Let's look at an example. Here you've got a carbon-carbon double bond. Those pi electrons, those are electron rich, and they can attack an electrophile, and the electrophile enters the molecule. There is a formation of a carbocation, and then sometimes you would have a nucleophile that would go straight away to attack the carbocation and to form the substitution compound. However, another possibility is that you have a nucleophile that acts as a good base and captures a hydrogen from the adjacent carbon, The hydrogen goes away without the electrons as a hydrogen ion, and the electrons are retained by the carbons, and you form a double bond. So you retain the double bond in the structure, but it's not in the same place, the same two carbons as it was on the original molecule. And when this happens in a benzene ring, so if you are not looking at an isolated carbon-carbon double bond, but you have that double bond is part of a benzene ring, this electrophilic reaction has a specific name, and it's called electrophilic aromatic substitution. And it is by large the most important reaction that benzene rings and aromatic compounds can have. We will explore electrophilic aromatic substitution in much more detail in the future. In the second year, for example, and inorganic and organic chemistry, we'll have full sessions dedicated to this. As a preview, the reaction goes as follows. You have one of the double bonds of your benzene ring attacks an electrophile. Then the reaction could go two ways. There's a formation of the carbocation and the addition of the electrophile to the structure of the benzene. If now a nucleophile attacks the carbocation, you would end up with a substitution product, in which an addition product, in which the aromaticity would be lost. You would not have the three alternated double bonds. That's not happen. Because the benzene ring is so stable, and that aromaticity makes the benzene ring such a stable compound, the aromaticity is restored. And the way it is restored is by the presence of a base that takes away one of the hydrogens in the carbon where the electrophile is now sitting, and that those electrons from the hydrogen that is left behind go to compensate that positive charge, and the final compound is still the benzene ring, but with the electrophile as one of the substituents, and that is called electrophilic aromatic substitution. In electrophilic aromatic substitution, it is important that the electrophile is really good. Benzene is a very stable structure. Those electrons are involved, those pi electrons are involved in the pi skeleton of the benzene ring. They are not particularly keen on reacting with anything. So for the benzene ring to react, to attack an electrophile, the electrophile has to be really, really good, really, really attractive, really, really strong to be subject to that attack. And typically, the electrophile in an electrophilic aromatic substitution is not added straight away to the reaction mixture. Is usually generated in situ, where the reaction takes place. For example, to nitrate, to add a nitro group to a benzene ring, you do not add the nitro group as a reagent. What you add is nitric acid and sulfuric acid, which react with each other to produce the nitro group, and once produced in situ, that is what is going to be attacked by the electrons of the benzene ring.